little embarrassed by the introduction. Thank you. And it's so nice to be here, and also thanks for welcoming me here. It's lovely to spend the year in Cambridge with people I both work with and also, just getting to know. So that's fantastic. Thank you. So I'm also really excited about the state of this project. That's a big project in Cambridge and in the UK. And it started 8 years ago, roughly. And now that we're at the stage of sort of starting to get early data from it, it's just a really exciting time. And it's also exciting to be with many of the team here. This is a picture taken from the site in Chile. So we are I'm going to acknowledge before I even get anywhere that this is anything I show comes from this great team of Simons Observatory collaborators. We are nearly 400 people at more than 60 institutions, more than 15 countries. And this was us in Chicago this summer. I think people in the room, I'll mention them in a moment, were there. And up top is some of our major funders, but there's a lot of contributions from institutions too. And I want to highlight, and I will maybe keep highlighting, that a major component of our mission here is actually public data and software, as well as the science that we want to do. And so this is one of the biggest teams, one of the larger teams actually is here in Cambridge. Many of you, I think, are in the room. I've just listed who I think are the Cambridge team here. And Cambridge actually has a unique situation that I think with Irene and Inigo, we've got the first and last members of the membership database of 400 people are in Cambridge. So you bookend the ESO members. We're also really grateful to Hiranya and to George for serving on our external advisory council and giving us wise input. Okay, so the story starts here. We have this beautiful image from Planck that I now see on my way into the cavity every morning, made with such effort from here in Cambridge, of the cosmic microwave background, our image of the universe as it was at redshift of 1100, capturing the tiny fluctuations in the universe at that time that will then go on to produce the first stars and galaxies. And this is, our state-of-the-art image of this time, of this epoch. And George and Anthony and well, I can't mention all the people here, have contributed to making this image and then also extracting cosmological information from it. And you might think it was finished, but we don't think it's finished. This field of exploring this early image of the universe, this image of the universe at that time, actually has so much more to get out of it that we can get out of it with new instruments, new observations of this epoch, basically. And so here is the place where the Simons Observatory now is. This was a picture taken 5 years ago. It's of this wonderful site in the Atacama Desert, which is ideal for observing the cosmic microwave background. So we're observing light that's been, it's coming to us from redshift of 1100. It's now in the millimetre wavelength. And so to take observations, we need to be measuring that wavelength. And we haven't currently got a satellite in this field, right? Our field of making these observations is currently working on the ground. We don't have a satellite right now. And so you have to think about where to go to do that. And the two best sites currently developed are in Chile. This is the site in Chile, and at the South Pole. And you want that because you want it to be dry, because we're looking through, it's water vapor that can really, mess up our measurements at these kind of wavelengths. So up here, it's at 5,000 meters. It's incredibly dry. And this was our previous telescope, the Atacama Cosmology Telescope, that many people here work on. We're actually finishing the final results at the moment. So that's not what today's talk is about, but I will be showing some things from it. And here are our neighboring telescopes, CLASS and Simons Array. But this whole plateau was empty 5 years ago. So now I want you to imagine walking up this path, up Cerro, and then looking back. And this is what it looks like today, up that mountain. this is this huge flat piece of the plateau that was empty 5 years ago. And this is now the Simons Observatory on this plateau here. This over here was the Atacama Cosmology Telescope. It's now being readied to actually host a bit more of the SO site. In the team, we sort of we refer to this project as SO. I'll probably be calling it that sometimes as I speak. And just to kind of give a flavor, what are we doing here? We're basically doing a new polarized millimetre-wave survey and covering half the sky that you can see from Chile. Some of the telescopes are looking at less sky, and I'll mention that. But that's roughly what we're thinking of, is this new survey in the millimetre that has 5 times the resolution of the Planck satellite, because you can put a really big telescope on Earth that you couldn't send into space, and of order 10 times lower instrument noise. But what I want to mention is that actually, because we're working from the ground with these observations, the Planck data will continue to be truly a legacy data set going forward, because the large scales that Planck could see from a satellite will continue to be the best measured for the foreseeable future. So any science we're going to do from this new observatory will generically include Planck in many of the science cases. Okay, so what are we kind of doing? You can sort of think of the science that we want to do from SO as coming much of it is coming from actually the primary CMB anisotropies, so the physics of the universe at recombination and before, that we can extract from making better measurements. But a lot of it is going to also come from secondary CMB anisotropies that come from, the CMB photons travel through the universe to us, passing all the large-scale structure through on their path to us. And we actually had a fantastic workshop here in September, organized by Fiona and others, where we discussed these things at great length. So we have late time effects, and also a whole bunch of millimetre-wave sources. This is a millimetre survey. You get the CMB, but you get other stuff too. And then, I just want to highlight that this idea of it being a community thing of making public data and public software is really sort of intrinsic to what we're all about. Okay, so just want to go to think about first the primary CMB, the image that we're used, you can see from the Planck satellite up here. And the typical statistic that we extract from the data is the variance in this map up here, or its power spectrum, as a function of the angular separation on the sky, or its multipole and spherical harmonic coordinates. And you see up in the orange, the beautiful measurements by the Planck team, much of that happening here, in terms of the intensity of that signal. And then down, quite a bit lower, we see this anisotropy signal coming from the polarization of the CMB, also measured really well by Planck. And the CMB, if you can imagine going back to the time it was formed when the universe was 400,000 years old, the intensity of the CMB more or less predominantly captures the density of the universe at that time. We're seeing the fluctuations in the universe at that epoch. And the polarization, or at least this dominant E-mode type, which is a kind of divergence-like part of the polarization, it captures the velocity of the plasma at recombination at the time the CMB formed. So if we could go back, if we're thinking about what can we measure with polarization of the CMB, predominantly you're seeing it tracks the motion of electrons at the time that the CMB is forming. They're kind of falling into potential wells and emitting polarization at that time. And that signal, that polarized signal, which is here, also measured beautifully already by Planck over many scales, it actually gets gravitationally distorted on its way to us. And this is a huge effort of understanding it happens here, and produces these kind of curl-like B-mode polarization patterns, which are here. Okay, the projections of how well we could measure all this stuff from Simons Observatory is in the blue. But we made this sort of realization when we were designing this project that you can't do it all. If you want to basically measure all this signal better, well, we acknowledge that we can't actually get to the very largest scales of all the kind of 90-degree scales from a ground-based instrument. That's not what we're trying, or not from our ground-based instrument. But you can't even do all those scales with one single telescope in Chile. And so what we what ended up being the path was think about the fact that on smaller scales, so, well sub-degree scales, these improved measurements we would need to make by doing a really high resolution survey of as much sky as possible with a large telescope that gives us high resolution. But if we want to get to kind of degree scales in the sky, we would need dedicated telescopes that really are focused on how to measure those large scales. And these would come from low resolution measurements. And I will go into this, why we care so much about getting to large scales a lot, and it's because of trying to look for gravitational waves, but I'm going to talk about that in more detail. So anyway, the program of SO is to have this big telescope measuring high resolution and small telescopes measuring degree scales. And the high resolution stuff gives us way more than just primary CMB, and I'll also mention some of those things. That didn't actually come out right. It's not a 0 meter. It's definitely not 0 meters. 0.4. That wouldn't work at all. Okay, so this is I love this. We've all been showing it a lot in talks because we all love this drone shot, right? This is a recent drone shot of the site from above. And so this thing of to measure the large scales, we have these three, this should read 0.4 meters. 0.4 meters a half, that big. Small telescopes inside these, we'll look at these in a bit more detail, doing a sort of deeper survey of the sky. And down here, this is this new 6-meter telescope that gives us the high resolution to measure the small scale features. They're all polarization sensitive. So all of these telescopes can measure the intensity and the polarization of this of the CMB. And the wavelengths of the detectors that are inside them are between 1 and 10 millimeters. And that's what we've determined is what is ideal from the ground for actually measuring the CMB and distinguishing it from galactic and extragalactic emission. Although it also gives us neat other views in those wavelengths. And then the big advance of this whole program is just the sensitivity. There are nearly 70,000 detectors in these telescopes, which is about an order of magnitude more than our previous project, for example, ACT, and similar other projects like the South Pole Telescope. And it's beautiful. I'm not involved, I work closely with colleagues who are involved in this technology. I don't do it myself, and I'm in awe of the incredible developments that have happened. And one of the neat things that I think is just quite elegant is that all the detectors in all the telescopes have the same fundamental detector module. So this is a picture of one of them. This is we call it a universal focal plane module. It's about that big. And it's got about 1,800 detectors on each one. They're bolometers, superconducting bolometers. And you basically combine them together to put into each telescope, and then the same thing that you put into all the telescopes. And you read them out all in the same way. And so that just simplifies the technology and then also the data analysis because it's all kind of common stuff. These two of these small ones had first light last October, November. The one in the middle is a higher frequency one focusing on dust that had first light in September. And we have a lower frequency one under development. And then this one is, and I'll say more about it, it's not yet taking data from the sky, but its camera is inside and it's kind of soon ready to go. So these ones are still commissioning, but we've got quite a lot of data to be looking at, which is exciting. Okay, so let me first get to this. Okay, let me talk about what we want to do and why with these small telescopes. And the thing, this was a great motivation of building the Simons Observatory. The major funder, I called out the major funders, but really the dominant support that got this going has been the Simons Foundation. And Jim Simons was very passionate and interested in this topic of trying to find out if we can see signals from the early universe, whether we can test whether inflation happened, whether we can try and rule out or find non-inflationary scenarios. And so the biggest target of those small telescopes is to try and look for gravitational waves. And gravitational waves generated during the first moments of the universe's expansion, whether it be, and whether it's inflation or characterizing inflation. We haven't yet seen them, but certainly inflation models would say that they were there. Okay, so the question is, if we have like some perturbation to the metric written up here, do we actually have, are there any visible tensor fluctuations that were put in the early universe that would then have propagated as gravitational waves? So far, they haven't been seen. And we characterize them by this tensor to scalar ratio R, which says how big are the fluctuations in the early universe that come from tensor fluctuations, propagated as gravitational waves, compared to the regular scalar fluctuations that we know and love and produce us later on, right? We have the scalar fluctuations are the things that the density perturbations, you get the density perturbations, they grow, they make galaxies and stars, and then later us. That we know those are there. We just don't know if there are any tensor fluctuations that would have then propagated through space as gravitational waves. And so the upper limit right now is that in terms of the kind of variance in tensor fluctuations in the early universe, the most it can be is 4% of the larger scalar fluctuations. That's the upper bound, and that's coming from the leading observations from the South Pole. So that was the other great site to be at is the South Pole. BICEP Keck have this upper limit of 4%, and especially combined with the Planck data, again, much that done here, we have a limit. We have this this tensor to scalar ratio, and this NS is the scale dependence of the scalar fluctuations, the density perturbations. And any inflationary model has a prediction for where in that space one should be. And this blue curve is the current upper limits in the community from BICEP Keck and also combined with Planck. And it's already ruled out a bunch of inflationary models that make predictions that are higher. These are different shapes of an inflationary potential, and they're gone now with this data. And so what we're trying to do with the Simons Observatory is push down the limits of where we are now, sort of a few initially by a factor of around 5 times lower in terms of where we could actually see these things. And again, I'm showing you what the signal is that we're trying to find. This is now the variance in the B mode signal. So this is now a handed curl-like polarization signal. If there were gravitational waves passing through the universe when the CMB formed, they would have polarized the CMB in all different manners. They would actually produce both E mode, kind of divergence-like polarization, and curl-like B modes. But the E mode part would be hidden underneath the much bigger perturbations from the velocity of the plasma. So the thing we really look for is this B mode signal. And the expected signal for different values of this R scalar ratio are shown here. This is the current upper limit from the BICEP Keck data. And these are the BICEP Keck data, the current state-of-the-art data points. And what I'm showing here is their sort of total signal measured at 95 gigahertz, which includes some contribution from galactic emission from dust. That's sort of those gray points. And then the kind of estimate of what the actual CMB signal is in the blue points. And there's no evidence for anything that departs from this black solid signal, which is no gravitational waves, purely just the scalar signal that's been lensed. And so the uncertainty there's an upper limit of 4%. The uncertainty on this data is about 1%. And we are trying to basically reduce that by a factor of 5 down to an uncertainty of 0.002, 0.003. Really, we'd like to be able to detect, if the true level is down here at kind of 1% or of 0.01, 1%, we want to be able to detect it. And so we basically be measuring in very similar angular scales to this existing data, but with the more detectors just trying to go deeper and see if we can see anything. Okay, so let me say what's happening. On the sky, this is now the sky in equatorial coordinates, the galaxies here. The bit of the sky that the bicep Keck data look at that I just showed you is down here, this orange. And the patch of sky that we're now looking at with SO is this region here, roughly. And so what has to happen to do it? And again, this has been the most extraordinary amount of work by many, many people in the collaboration. This is a picture of one of these kind of 0.4 meter diameter little telescopes. So you have 3 of those sat inside these. Okay, so those are ground screens. They're shielding you from kind of emission from the mountains around. So you put those inside those ground screens, or this is one inside it. And then you basically pack it in with loads of detectors. This is the back end. These are kind of 7 of those UFMs, these detector modules, all tiled together. This is actually, one of these was assembled in Princeton, and this is the Princeton team in Chile reassembling it. It was actually kind of awesome to watch them go through the whole assembly in Lyman Page's lab in Princeton, get it all working, pack it all up, ship it to Chile, unpack it all, and get it all working. It was as someone not involved in doing that, it was extremely impressive. And this is just one of the 3 of them. Anyway, okay, so we've been taking commissioning data, and these are some early results. It's early maps, still preliminary maps made by a whole set of our team members. This is just a picture of the galactic, along the galactic plane. So here we are, galactic longitude and latitude. And here we show like Q polarization Stokes vectors, where this is polarization oriented like this. And U is over here like this, Q and U Stokes vectors. SO and Planck are really seeing rather similar sky. It's looking quite consistent. And you're seeing like a whole bunch of we're used to this from the Planck data and from much data. You see a whole bunch of positively polarized signal there, and it's coming from dust in the galactic plane. But we're seeing that in both of those. And then there's also the team have been hard at work, and we have some preliminary CMB polarization. It's not the galaxy, but actually just a small CMB field, where what I'm showing you here are again Q and U Stokes vectors and maps of a patch of the sky. And I hope that your eyes can see the top one looks like this and the bottom one looks like this. The lovely thing about this doing these measurements is that we all know that's what we're looking for. So when you're trying to first analyze your data, when you're starting to get data in, if it's noisy or you've got the angles wrong or the pointing wrong or something wrong about your data analysis, you won't see this. And then when you do see this, you know that things are at least on the right track. And let me explain why. It's because the dominant polarization signal in the CMB is, as I said, from the velocity perturbations at recombination. And its particular pattern is an E mode, a divergence-like polarization that you can imagine to be polarization that around any point is either pure radial or pure tangential. So this is the kind of signal that we're looking for. The Stokes, in the orientation, you define these Stokes vectors in an orientation of your observations. And they're defined such that the Q is like this, again, and the U is like this. And the Q then, an E mode has Q variants there, 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 and there. And it has U variants there, 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 and there. So if you're seeing an E mode, you see variance in Q that looks like this, which indeed you're seeing up there. And if you're seeing a variance in U that looks like this. If you had equal amounts, if you had noise or equal amounts of both E and B, you wouldn't see any particular direction. So anyway, it's been a fun process just over the past months with the team of collaborators kind of trying to see whether we see this signal. And so this is just kind of like, and if you got the polarization angles wrong, this would all be like tipped a little bit. So anyway, everyone's sort of quite excited about this. This is not, of course, the gravitational wave signal we're looking for. The B mode is hidden way underneath this. The thing we're looking for is deep underneath this. The scales are bigger than this. These are smaller, slightly smaller scales than the signal we're looking for. So this is just something that's just beginning. It's not in full. It's not even in full survey mode yet with the observatory. Okay, let me just mention. I do want to mention. I'll move on in a quick moment, but I want to mention the one of the critical things that you need. We've determined that we need in Chile if you want to measure a degree scale signal on the sky. So the thing we're looking for, the gravitational wave signal, is again sort of degree scale-ish and larger fluctuations. But that is really hard to disentangle from the atmosphere in Chile that is moving past as well. So these things scan at about like 1.5 degrees per second through the sky. And you have atmosphere in Chile, can't help it, even if it's dry, it's still there, that is also correlated on those kind of timescales. And you're trying to pick out a signal that has the same kind of angular scale as the scale of your noise from the atmosphere. And so what we're doing is modulating the polarization signal by spinning very rapidly a half-wave plate made of sapphire that spins really quickly. It's birefringent, and so it modifies the polarization angle of the light as it comes in, and rotates the polarization angle. And it does it 4 times every time it spins. So if you spin it at like twice per second, it modulates the polarization signal at 8 times per second. Why does that matter? It matters because that frequency, if I imagine taking like observations as I scan back and forth with time, I can imagine plotting like sort of the noise level against time. And actually some raw data might be like fluctuating like this with a long time scale. If I Fourier transform that and say, what does the noise of that look like? It has this black curve here where the noise is very not white at these scales. And these scales, at 10 seconds kind of time scales. But if you then modulate the signal with this rapidly spinning half-wave plate, and then you demodulate the data, you could undo it in software. Then this is just a preliminary curve of some of the early data where you get back this kind of white noise level where the scale you care about is now not dominated by atmospheric noise because you've done this clever modulation thing. I also kind of just love that it's done on this superconducting, levitating bearing. It spins this half-wave plate incredibly fast. It's beautiful technology that is currently in all these telescopes. So that's part of the critical thing of what we have determined that you need to make this work. Still obviously under investigation. Okay, so that's a quick update on some things from the small telescopes. This is the big one, the Large Aperture Telescope, which is not yet observing for some obvious reasons that it doesn't yet have its mirrors in. Okay, so it's a 6-meter diameter telescope with actually 2 6-meter dishes. It's since got some shielding around it, but this picture lets you sort of see inside. The light will come in, then bounce onto a big 6-meter mirror down here, bounce onto a secondary, and into here, which is this giant camera. And so this is the receiver cabin. And inside there is truly an enormous millimeter wave camera. It's 10 times sort of bigger than we've generally dealt with before. It's got, I'm doing this because that's how big it is. The diameter is my, my arm span. And there's a picture of it here. And that's actually currently inside this receiver cabin. It's already there waiting for the mirrors to arrive and be put in. And here what you have again is just even more space where we've packed in those same detector modules with this same kind of frequency array into this larger camera. And this is a whole bunch of the amazing team who've been doing it. So this survey is one that I hope we all hope that the community will actually make great use of. It's going to be this half-sky survey at, a few times the depth of where we currently are with our Atacama Cosmology Telescope depth, and really filling in this whole half-sky with uniform coverage. So even over the galaxy, if you care about, if you're interested in galactic science, which many people are, I am too, it's going to give this sort of uniform depth over this whole swathe, fully overlapping with Rubin, and with quite a lot of overlap with Euclid and DESI. And so you can imagine what you'll get is like a half-sky image of the CMB. This is a little snapshot of where what we see in temperature and polarization with ACT. The depth is just going to be deeper. It's going to be more sensitive, higher sensitivity. And this is where, so there is a ton of interesting kind of primordial, early universe science to be done with it. But I just want to mention some of the later time science that I think is really interesting. And again, we had this great meeting here in September about some of that science. So I won't spend long on this because here you've got all the experts in the room. A couple of one of the really interesting areas that we can weigh in on with the secondary CMB signals is the growth of structure. Do we see the growth of structure over the age of the universe behaving as we would expect in the lambda CDM model? Can we see any departures from it? Can we measure the equation of state of dark energy or the neutrino mass? And two of the ways are first by measuring the gravitational lensing of the CMB. And again, this is a huge, the Cambridge have this huge, expertise in this area. And in fact, this image came from, the group here, plus collaborators in the US. This was the kind of, this is what you can expect more and better of, given that this is a beautiful image. So this image, the purple and orange, is a map of the lensing potential of the CMB, so an integrated dark matter map across the sky that we could see with the Atacama Cosmology Telescope. Imagine that with SO, you'll get, you fill in these gaps down here and make it even more sensitive. And you'll basically get this map, and here I'm sure I know that this will be happening a great deal here in Cambridge, will be this improved map of the dark matter that can then be correlated with other things too. The second way to probe structures is by looking for big clusters and seeing how they form over cosmic history. And again, that's another thing that's happening here in Cambridge. We see clusters via the Sunyaev-Zel'dovich effect. The hot gas in them scatters the CMB and shifts the frequency dependence, such that if we look at a little snapshot of the CMB at a given frequency, a cluster shows up as a cold spot there. That's a galaxy cluster. That's like a 2 times 10 to the 14 solar mass cluster or so. These are like degree scales on the sky. I've lost my pointer. With ACT, we had the sensitivity to see in the latest catalog from our collaborator, Matt Hilton, has about 8,000 clusters with redshifts over half, nearly half the sky. And that will go up to about 20,000 with SO, with this kind of predicted number density as a function of redshift, where you're really getting clusters out to redshift 2 and beyond. And so the lovely thing about being overlapping with optical surveys is you can weigh your clusters with optical weak lensing and other combinations, and you can check you've got your cluster masses right to try and look at the growth of structure. Now, we sort of, the thing that we, I think, have become even more excited about, I think in the last, I would say the last few years, and again, we talked about this a bunch at this meeting here is, and this again, you've got all the experts here, is being able to map the baryons. So you can combine, you can not only find the clusters, you can combine the multi-frequency information in a way to actually make a map of the gas pressure across half the sky. So you not only see the big things, but you can see, if you look carefully, you can see, more detailed structure. So this is a map made by Will, who's now here, Will Coulton, for the ACT collaboration. Again, you can imagine this is, oh, I don't know what's happened there. But anyway, so what you're seeing is like the bright stuff is where you've got hot gas. It's a map of the pressure of gas. And a nice analysis took this and stacked it on dark energy survey selected galaxies and oriented them to look for superclustering, to look for, large filaments. And this is an image up here from this paper where you're seeing this stack of the sort of gas pressure on top of DES galaxies, but you also see this extended structure of gas out much further that's basically probing the large-scale cosmic web. And then the other thing, and then we also are able to measure not only the gas pressure, but just its momentum, which gives us a sense of just where the baryons are. So you can actually measure via the kinetic Sunyaev-Zel'dovich effect. You can actually measure where baryons are out to much higher radii around galaxy groups than you can with many other techniques. And again, this is a recent result from ACT that we're just going to improve upon with SO, where this is the kinetic Sunyaev-Zel'dovich effect signal stacked on loads of DESI galaxies. And you look at the cumulative signal as a function of radius, which is here in red. And this shows you basically how the gas is distributed around galaxy groups. And the key result from here is that actually it turns out, for example, that this gas is pushed out. The fact that this green curve, these red points are below this blue one, says that you need basically more feedback from your feedback going on to push out the baryons further than you might expect in some simulations. So I think many of us, and Alex, Amon, and Leah, and other people here are busy working on this. This idea of being able to actually use a large-scale map of the baryons to figure out what's happening with feedback. And again, I think many people appreciated how important this was, but I think this has become particularly important as we're trying to understand small-scale clustering of matter. Okay, let me get on to my last thing, which is, this is a snapshot again of the CMB seen by ACT. We see something similar with SO, but deeper. There's lots of red points. You see lots of red points. These are all AGN, or mostly AGN, lots of dusty galaxies. What I'm very excited about is that you can find them across the whole sky, or half the sky that we see from Chile. It's just like an image from our colleague Sigurd Ness of all the sources that we've seen with ACT already. More than 30,000 extra, AGN or dusty galaxies. But the thing that we didn't ever think of doing really before, and has now become a big part of the SO program, is variability in time domain millimeter science. This is an example of an AGN, again, seen from ACT, but we will get more of them and with better cadence in SO, of how an active galactic nuclei is varying over 4 years in a whole bunch of millimetre wavelengths. And to have that in addition to other observations, the millimetre actually these are basically blazars, jets firing at us. And you can, I think, see better into the inner part of jets than you can with longer wavelengths. And also you can search for example, binaries. There've been beautiful, possible binaries seen by the OVRO campaign at lower frequency. So what we're going to do is track thousands of these and make daily maps and release fluxes of them every day or every week or every month so that people can actually be gathering that data themselves and comparing it to other observations. And we've sort of committed we have support from the National Science Foundation for this. We're building a pipeline. We're kind of building up to having, hopefully from 2028, just be streaming out these AGN fluxes, to give light curves for all of these things, which I'm just really excited about because of the way that they can be then absorbed into other wavelength, multi-wavelength model fittings. We're also going to be looking for things that are just purely transient events. The first things that we've seen in these kind of surveys are flaring stars in the Milky Way. This was an example, again, from ACT of like 14 flaring stars that we found in the data set when we went back and looked at made maps at a regular cadence. And with ESO, we expect to see about 100 of these per year. And we've really designed the cadence of ESO to be able to be regularly going back and surveying half the sky. So this was never something we thought about for our old ACT telescope, was the cadence. I know that people who work in time domain obviously would be like, why didn't you think of that? We didn't think of that. And now we've designed the ESO cadence to be basically to be regular and roughly every between 1 and 3 days to revisit half the sky. So it's this really regular return. And again, we're building our pipelines to be able to catch things quickly and turn them around and issue alerts, which again, our current model of analysis has been gather 5 years of data, analyze it after 5 years, and then find some transient events. It's not so useful if you want to actually go and compare it to observations. And then we're really hoping that we will see extragalactic transients. I'm hoping I see them. I think I pulled out the cable. No, I didn't. Did I? It's back. Awesome. And I'm delighted that Martin, you're here as well. So we think this is not my expertise. We're really trying to build expertise in the collaboration actually, because it's very few of us have expertise in these objects. We think that the most likely event that we will see in the millimeter is gamma ray burst afterglows, and in particular ones that have reverse shocks that have been showing up in our wavelengths in other data. Per daily observation, we'll have about kind of, depending on upgrades, about 5 to 10 millijanskis sensitivity on a daily observation. And the projection is that we might be seeing roughly like 10 reverse shock gamma ray bursts each year. Again, there's no confirmed extragalactic millimeter sources in our current surveys. So we're sort of like, there are these lovely projections in these papers, but we're not sure if that's what we're going to see. And again, this is where I'm not at all the expert, but my understanding is that being able to see these so you have forward shocks and the reverse shocks, and being able to see these reverse shocks tells us more about the gamma ray bursts. Again, I will be delighted to hear from experts. And this is just some examples of recent papers where, for example, this is the frequency we observe at. These are some sort of light curves from, or predicted emissions from, one kind of, just a forward shock and a reverse shock, and being able to actually measure at this millimeter wavelength can actually distinguish between models. And we discovered yesterday that data from, the Cambridge AMI experiment has also been used for this at 15 gigahertz to combine it with higher frequency data on this other gamma ray burst to try and distinguish exactly between different models. So that's really neat. And so I hope we'll be seeing these things and that we can catch them in, the first hours after emission and be able to distinguish between different objects. So this is we're kind of trying to build expertise in our collaboration, but also with the view of we're just going to release the data. These transient alerts will go out straight away. We want the community to be able to use them. Okay, so where do we go beyond that? We are finally building, thanks to the National Science Foundation, a solar array up there to stop burning quite so much diesel. So currently we transport diesel up there and run it from diesel power. And so the solar array will be a fantastic step forward for green energy at the site. We'll get this working, I hope, in the coming, it's due to start observing in this coming year. And again, these ones should be then, entering regular operations in this coming year as well. We're adding some detectors to the big telescope over the next few years. And then really, excitingly, I think in the UK are building 2 new small telescopes. We've got 3 here. The UK are, with people very much here in this group too, building these 2 new ones here and here that will just increase our sensitivity to primordial gravitational waves. And Japan are also building one that's going to give us the synchrotron measurements, and that will go on the old ACT site here. So this site is really, ripe for expansion. It's the place where people really are discussing what's the next generation, CMBS4, or the next stage would basically to just expand this site for more and better science. But in the near term, we're really excited. And again, it's gone black. It's fine. It's good timing. This is a huge team effort. And again, I acknowledge all the people here as well who are involved. So thanks.
Okay, thanks ever so much, Jo, for the wonderful talk. Do we have any questions?
Silence, G.
Deborah.
So, yeah, thanks for the wonderful talk. So I have a question on this really intriguing but very puzzling case.
Yes.
And the implications for feedback, removal of barriers, and so on.
Yeah.
So what is your take on, so there are some simulations that can predict much bigger effect and more in line with the estimates that you were showing. Most of them struggle. But there is also this conundrum of matching the gas fractions from the X-ray data.
Absolutely.
You have a considerable scatter, but there is a population of objects that do have relatively high gas fractions, even going towards groups.
Yeah.
So what's your view of all of this?
I mean, yeah, I think the good view is that we're adding data to the, we've got X-ray data. This adds, we've got both this information and then the TSE as well, which is probing more in the center of, more close in to the groups. And so I think we have to, and I know that, again, I know that you and others are working on this, that doing these joint, we have to figure out how to correctly include all that data in comparing to simulations. But I think this is, so the fact that, again, that the amount of the distribution of the baryons is consistent with the illustrious simulations, but I know that there are problems. They don't fit the other data. So there isn't currently. Exactly. So it's ruled out by the data. But I think it's probably then a question of, it's not all probing the same masses, I think. That's the masses and scales are not all the same. And this is, I think, something that I know that Leah, who I'm not sure is here, is working on. Probably, with you, right? Exactly, with you. So it's not clear to me whether you could come up with a solution that changes how things behave as a function of mass. This is kind of these are stacked on like 10 to the 12 solar mass objects. I agree, there's not yet, of course your question should be, is there a problem with the data? That should always be a question, right? We are seeing the same thing. It's the same data set. We're seeing the same thing, something pretty consistent with previous stackings, different frequencies of these maps. But I think it's still, one should always question analyses and try to make sure they're robust. There have been quite a lot of robustness checks of this, so I think it should be taken seriously, but at the same time, we should be always, one should always be questioning the data. But if it's there, it's there, it's there. I guess to fix the simulations, I don't know. Yeah.
Win.
So what are the millimetre transients that you have discovered?
Very good. So far, we have only discovered flaring stars in the Milky Way that. Which is super interesting, but that's the class of them basically. So and so they've been matched up with known stars. So we've seen like 14 or so, and SPT have actually seen, South Pole Telescope have seen even more. I've now forgotten what distribution of which stars they are, but that's what we've seen so far. Okay. Yeah, we haven't seen. There was one South Pole Telescope kind of event that may have been a gamma ray burst, but there's not certainty over that.
So are they very young stars? Are they T-Tauri stars, or are they M dwarfs? Or?
They are, I think, M dwarfs, and yeah.
Thanks very much for the really nice talk. For the high cadence observations, it was very exciting. Could you say a little bit about whether you get that same sensitivity every 3 days?
Yeah.
Over the whole sky, or whether it's concentrated?
No, whole sky.
Right. And what is the redshift range that you would be sensitive to with this data?
Oh, that's very interesting. I guess I have in my head just a Millijansky rather than redshift. So I don't probably know enough. Yeah, okay. Yeah, I can tell you exactly, sort of roughly a bit lower than 10 Millijanskys, but how that converts into the redshift. I mean, people have done these studies, but I don't have this in my head. But how they convert into redshift, I'm not so sure. But I know, it's sort of not embarrassing that, Rubin, of course, as you know, will have so many events that this is actually the likely number is actually very small, but then I hope that we would then be able to match them up to Rubin transients.
George?
Yeah, so going back to the constraints on feedback, I think there's a scale issue, interpreting X-ray measurements in addition to the large scatter. So I would turn the argument round, and say, use KSZ, thermal essay to constrain feedback, and then try and interpret the X-ray data.
And again, I didn't, And what I was sort of skimming past, but this KSZ measurement is the most rapidly increasing signal to noise part of the CMB. So it should shoot up to 100 sigma measurements. There are different ways of probing it too. So it's that's partly why, if we also, we wait a bit for the DESI, stack on the DESI 3-year signal, then add in SO, and then it's going to, there've been some, curves of how this improves. So there's not a solution. I'm just saying this measurement will increase significantly and also allow you to split it up more by mass and by, stellar mass and other redshifts. And so we'll actually, I think, have a more varied data set to be able to fit simulations to, rather than just one curve, for example. Yeah.
Craig?
The quality of the polarization data is going to be very critically set by the rotating half-wave plate.
Yeah.
Can you rotate that at different speeds to check how consistent it is and whether it's really working properly?
So one of the things that's been done is change the direction of it, and that's one thing. I think, do you know what? I know that someone knows the answer to this, and I don't think I do. That there was a choice to set it at that speed. I think it can be changed speed. It can be changed speed, but there was some choice to set it there. But there are being tests of certainly different directions.